In the last section, we looked at confidence intervals for the population mean. But we focused on the idea that the standard deviation of the population was a known value, or that our n value was bigger than or equal to 30, so we had a large sample. But what if neither one of those is true? What if our standard deviation of the sample is an unknown value, and our sample size is too small? Well, first let's talk about a t-distribution. We're going to use a t-distribution here. The reason is because our standard deviation is unknown. We have to use the standard deviation from the sample. The fact that we're looking at that from a smaller scenario means there's a lot more variability in that. It might not be quite as accurate. So we're going to use this t-distribution. A t-distribution very similar to a standard normal distribution. Okay, similar to the z-scores. It's bell-shaped. It still has symmetry around the mean. It still has the mean, and the mode all equal to 0 at the center, and it never touches the x-axis. But here's the difference. In a standard normal distribution, we know that the variance and the deviation are 1. That's not the case in a t-distribution. It's actually bigger than 1. It's more spread out. There's not just one curve. There's a whole series of curves, and we'll look at a table in 1 second that hopefully you downloaded. And as your sample size increases, as n gets larger and larger, especially once it approaches 30, the two start to look like each other. So we've looked at a normal curve a lot. The t-distribution curve looks pretty similar. The difference is it's not quite as high in the center, and there's a lot more space on the edges here because there's more chance for values to be extreme because we're only looking at a small sample. It's a lot easier to get an extreme value that affects a mean if we're only looking at 10 as opposed to 100. We're going to have what we call degrees of freedom here. And we'll talk more about that in a little bit, but our degrees of freedom is n minus 1. So if your sample is 12, you'd have 11 degrees of freedom. The formulas are very, very, very similar to each other. The only difference is in all these, sigma is taken out and the lowercase s is put in, z is taken out and t is put in. With the calculator, you can't really get t quite as easily as you could get z before. So what we're going to look at in a second is the idea that there's actually a table for this. And please print out that table. It's also on the site. Okay. So Jack is opening an ice cream shop, and he wants to ensure that his price for a large cone is comparable to the mean of the shops in the area. Well, he's looking at 15 shops. Average price of $3.14. Standard deviation, this is of the sample, of 59 cents. Now this is a t-distribution. We don't know sigma, so we have to use the standard deviation from the sample, and our n is smaller than 30. So in this case, we're going to have to use the t-distribution. Well, the first thing we do is we find our degrees of freedom. Our degrees of freedom is n minus 1. So in this case, our degrees of freedom is going to be 14. If you would at this point, go to the table provided. At the top, you'll see where it says one-sided or two-sided. Our confidence intervals are going to be two-sided. Find the column that has 95% for two-sided, and work down that column until you get to 14 degrees of freedom. You should see the number 2.145. That's the number we're going to use to find our confidence interval. Everything else about this is identical to the problems we did last section. I'm still going to take my x-bar value. I'm still going to add and subtract a number. In this case, instead of z, it's going to be this 2.145 t-score that I found. I'm still going to take my standard deviation, but now it's from the sample. And I'm still going to put it over the square root of the population or sample size. Not the 14, but I use the 15, sample size. So the second question. Sample size of 28, which means my degrees of freedom is 27. I have an x-bar value of mean of 14.3 and a deviation from the sample of 2. 99% confidence. So go back to your table. Find the two-sided at 99%. Work down to 27 degrees of freedom. And the value you should see is 2.771. Now I'm going to go ahead, I'm going to plug that value in just like I did before. My mean plus or minus my t-score. Deviation over the square root of sample size. That's going to give me 14.3. My margin of error is 1.05 miles. So when I add and subtract it, I'm 99% confident that the true average distance that a person travels, that an employee travels, is between 13.25 miles and 14.35 miles. And then one final example here, N value 28, X bar value of $56,718, standard deviation of $650, degrees of freedom must be 27, N minus 1. I'm doing 90% confidence. So I look at my table, I work my way down, and I find a t-value of 1.703. Once again, I plug my information in. And when I put that all together, put the answer down here, I'm going to end up with $56,508.81 from my lower and $56,927.19 from my upper. So I'm 90% confident that the average salary, average yearly income, is inside that. So what should the faculty member use to see if she's being overpaid, underpaid? Well, it'd be unfair to use anything besides the lower in this case. So she should look at the $56,508.81. If she's being paid below that, she has an argument to say that she's being paid below the average.